Hi students, Miss Vernon here today to talk about lesson 2.6, day 1. We'll be spending 2 days studying the graphs of rational functions. Today we're going to begin by talking about how to analyze the rational functions, simplify or factor when necessary, and then eventually we'll be using long division to talk about transformations of some rational functions. So let's go ahead and jump in. A rational function is basically defined as the quotient or the division of two polynomial functions. So notice that in this definition, g and f are both going to be considered a polynomial function. That means that its exponents are all going to be integers and they're going to be positive. So one thing to remember is that if a rational function is simply a quotient, we're going to utilize some of those division skills that we learned earlier to help us analyze or kind of understand the way the graph will behave. So let's go ahead and jump in. I have 3 examples for us today. And in each of our examples, we will be not only analyzing it, but we will also be graphing it. So with this first one, we're just going to use our knowledge of functions to determine the domain information. We're also going to introduce a concept of limits to analyze how it behaves around a vertical asymptote. So to begin, I'm going to go ahead and recognize that if I were describing f of x, I would say that the parent function is going to be 1 over x. So remember, our parent functions, those are going to be our core group of functions that help us visualize what the shape of this graph might be. So if you remember, the 1 over x is our rational function, and it basically is, I call it my disco function. So we have our 2 groups there. Now, the next thing I notice about this function is that we're subtracting 2 and it's connected to the x term. So that implies that I know that this particular function is going to be shifted to the right 2 units. And so that's the transformation that is happening. Now, in the above information, it did ask us to state the domain of this function. Oops, sorry, my screen is causing a little bit of trouble there. And so as I think about the key features, I can state the domain, but I know that the key features are also connected to the asymptotes. So one of the first key features I notice is that I'm going to have a vertical asymptote at x equals 2. And I find that vertical asymptote is x equals 2 because I set the denominator equal to 0 to find it. Okay. I also know that it is bottom heavy, so I also have a horizontal asymptote at y equals 0. Again, that's because it's bottom heavy. Now, because I have this vertical asymptote, I know that the domain of my function is going to be everything except for that vertical asymptote. So therefore, it's going to go from negative infinity to 2, and then 2 to infinity. The other piece of information that I find really helpful is I like to find the y-intercept. Now, the y-intercept is found by plugging in 0 for all the x's. And so if I do that up here, I would have f of 0 equals 1 over 0 minus 2, or 1 over negative 2. So 0 comma negative 1/2 is my y-intercept. All right, now before I really do a ton, I'm just going to go ahead and graph what I know. So 0, negative 1/2, I'm going to put a dot there. That's my y-intercept. I'm also going to grab my line tool and I'm going to plot a vertical asymptote at x equals 2 and a horizontal asymptote at y equals 0. Next, I know that if it has to pass through this point and it has to follow the asymptotes, my graph will exist over in this area. Now, because it's a rational function, I know that it also is going to be opposite of that location. So it's also going to be up in that area. So without doing a ton of algebra, I was able to use my knowledge of graphs and functions to create that graph, right? What we're going to do next, though, is we're going to explore understanding the behavior near the vertical asymptotes. Now, in this particular function, we were able to use our logical reasoning in order for it to pass through the y-intercept and follow the asymptotes. It needed to exist in these areas that we've marked. But not all graphs are going to behave that way. So we're going to want to have a way to analyze or understand what's happening. And so to do this, we are going to use limit notation. Now, this limit notation is slightly different than what we've seen before. Before, when we've used limit notation, we had x approaching negative infinity and x approaching positive infinity. This is very similar still to what we saw before. We still are looking at what is the y value doing, but this time we're looking at as x is approaching our vertical asymptote. So notice that x equals 2 is the vertical asymptote. I'm going to use VA to represent vertical asymptote. What this minus sign up here is talking about, and I'm going to highlight it, is that negative sign up there is actually saying, so as x approaches 2, and then the negative sign is indicating from the left. So as I approach this number from the left side, what are my y values doing? Now, to analyze this, we just plug in a number to our equation that would be to the left of 2. For example, I'm going to plug in 1. If I plug in 1 for all the x's, I get 1 over 1 minus 2, 1 over negative 2. Now I care less about the number and more about the sign. So this gave me a negative number out. So I would say that as x approaches 2 from the left-hand side, my graph is going to continue to get closer and closer to negative infinity, or it's going to approach y values that are progressively smaller and smaller. Notice that if I'm tracing this, I see that my y values keep going smaller and smaller and smaller. That plugging in that number allowed for us to see that. Now, over here, again, notice that we are analyzing it still. X equals 2 is the vertical asymptote, but this time we are looking at it from a different perspective. We're looking at it from the positive direction. So that plus sign that you see is basically saying as we approach this number from the right-hand side. So what happens as we approach this asymptote from the right side of it? So just like we did before, we're going to plug in a number that is to the right of positive 2. In this case, I'm going to plug in 3. Again, I don't care as much about what I get out as I do about whether or not it's positive or negative. In this case, it produced a positive number. So therefore, I'm going to say that as we approach 2 from the right-hand side, our graph is going to keep approaching larger and larger y values that are positive. So notice that again, as we go, it gets more and more positive. That is how you analyze a function using limit notation and understanding what's going on. Let's do another example. This one is a little more complex, so I'm going to warn you up front. This one is a little bit more involved, but we're also going to be looking at it with the same lens. So again, we're analyzing the function, x-intercepts, y-intercepts, vertical asymptotes, and then sketching the graph. So the first thing I always look for when I am dealing with a polynomial is I try to factor it. The reason I try to factor it is because I'm looking to see if I have a common factor on the top and bottom. So the first thing I notice is that both 3x squared and negative 12x have a 3x in common. This leaves me with x minus 4. On the bottom, I also see that this is able to be factored. And I know that numbers that multiply to negative 3 are going to be negative 1 and 2, or negative 2 and positive 1. And I'm sorry, negative 3 and positive 1, or negative 1 and positive 3. I apologize. And when I do this, I see that -3 and a +1 will end up adding up to equaling a -2x. Next, I look to see if there are any holes. In this case, there is not a common factor on the top and bottom, so I'm just going to make a note that there are no holes. Next, I'm going to find my x-intercepts. To find your x-intercepts of a rational function, you are going to set the numerator equal to 0. So x-intercepts occur when the numerator, I'm going to just write this out, equals 0. So in this case, I would have to take 3x equals 0 and solve that, and x minus 4 equals 0 and solve that. So dividing by 3, x equals 0, and adding 4, x equals 4. These will be my x-intercepts of my function. So I'm just going to jump over to my graph, and I'm going to plot these points just so that I can build my graph as I go. Next, I'm going to find my y-intercept. This is just my system that I like to use. It helps me organize and not forget anything. To find the y-intercept, you plug 0 in for all x's. All right, so if I plug in 0 for all my x's, on the top I would have 3 times 0 squared minus 12 times 0 divided by 0 squared minus 2 times 0 minus 3. In this case, I get 0 over -3 or 0. This makes sense because we already had a point at 0, 0, so that made sense that that would be my y-intercept as well. Next, we're going to go ahead and determine our vertical and horizontal asymptotes. So my vertical asymptotes are found by setting the denominator equal to 0. So when I do that here, I would have x minus 3 equals 0 and x plus 1 equals 0. So x equals +3 and x equals -1. I'll go ahead and graph those vertical asymptotes right now as well. Again, just building my function as we go. So I have a vertical asymptote at -1, and I have a vertical asymptote at +3. So far, everything that I have graphed seems to be aligning with what we've learned so far. Next, I'm going to identify my horizontal asymptote. So my horizontal asymptote is the top heavy, bottom heavy, or same. So in this case, my highest exponent on top is 3x squared, and on bottom is x squared. So therefore, I would say I have a horizontal asymptote at y equals 3 over 1, or y equals 3. Again, building my graph as I go is just a tool I use to help me keep track of what I'm finding. So 1, 2, 3, we have our horizontal asymptote happening at y equals 3. Now that we have a good idea of what's happening with our key information, we need to go ahead and evaluate what's happening around the vertical asymptotes. So what I'm going to do is I'm going to go ahead and take this information and we're going to analyze it. Now, again, I'm going to remind us that we have our function, and I'm going to evaluate our function at the different values using my factored form, and I'll show you why I'm going to do that. It's just going to help us lead into future lessons, as well as focusing more on the positive and negatives instead of focusing on the number we get out. So that was our factored function. And if I'm evaluating around this first asymptote, I want to evaluate the limit as x approaches -1 from the left-hand side. So remember, a negative in the top corner of the number tells me I'm approaching it from the left-hand side. So to evaluate this one, I'm going to plug in, let's go with a -2. So if I plug in a -2 for x in each of my parenthesis terms, what I find is that a -2 in for the first parenthesis would produce a negative number out. A -2 minus 4 would produce a negative number out. A -2 in for x minus 3 would produce a -5, and a -2 plugged in for x would produce a -1. 4 negative values will end up producing a positive. So I know that in this case, as I approach this asymptote from the left-hand side, my graph is going to approach positive infinity. So I'm going to come up to my graph, and I'm just going to go ahead and graph this. So I know that as I approach this, it's going to go to positive infinity because we just tested it. And because it has to follow the end behavior of our horizontal asymptote, I know that it's going to level off around that 3. Okay. Continuing to build our function, I also need to evaluate the limit as x approaches -1 from the right-hand side. So again, I'm going to use the same kind of idea. This time I'm going to plug in a number that is just to the right. Now, I don't want to plug in 0 because we know 0 is an x-intercept. So I'm going to plug in the value of -0.5 or -0.5. When I plug that into my x's over here, a -0.5 into the first parenthesis is going to produce a negative. A -0.5 in for x minus 4 is going to produce a negative. A -0.5 in for x minus 3 is going to produce a negative. And a -0.5 into x plus 1 is going to produce a positive. So in this case, a negative times a negative is a positive, and a negative times a positive is a negative. So this ends up becoming a negative infinity. What that means is that as I approach this asymptote from the right-hand side, my graph is, my y values are going to get closer and closer to that asymptote, but they're going to be headed to negative infinity. Okay. Now, we need to do the same analysis moving into the next part. So we are going to have to evaluate around this asymptote. So we're going to go ahead and say, what is the limit? I apologize. Limit as x approaches the vertical asymptote of 3 from the left-hand side. So for this one, I'm going to plug in a number that's just to the left of 3. In this case, I'm going to plug in +2. Now, when I plug in +2 for the x, I'm going to get a positive on the first term. 2 minus 4 is a negative. 2 minus 3 is a negative. And 2 plus 1 is a positive. 2 negatives and 2 positives will become a positive. So as I approach 3 from the left-hand side, so as I approach this asymptote from the left, my graph is going to get closer and closer to positive infinity. As you can see, we're building the function as we go. Now, I kind of already have an idea of where the graph is headed for the next one because of where my x-intercept is and the asymptotes, but we're still going to test it out just to be sure. So for the final part, I need to evaluate the limit as x approaches 3 from the right-hand side. Now again, we have a 0 at 4, so I can't plug in 4. So I'm going to plug in 3.5. I needed to be between 3 and 4 in order to get an accurate representation. When I plug in 3.5 for all the x's in f of x, I see that I get a positive. 3.5 minus 4 is a negative. 3.5 minus 3 is a positive, and 3.5 plus 1 is a positive. So in this case, this produces a negative out. Therefore, it is approaching negative infinity. This is what I thought would happen based on where my x-intercept was sitting. Again, end behavior always follows those horizontal asymptotes. I did go ahead and graph this as well, so you could see if our graph resembled what we saw here. And as you can see, it does match. Again, this is a little bit of work, but definitely something that is worthwhile and you are definitely capable of doing. I have one last example for you, but we'll go quick through it. In example 3, I want to dig in a little bit more to when we have a whole versus when we have an asymptote. This question's come up a lot in our lessons. So I have two functions here, and we are going to evaluate them in the areas that we learned from before. So we are going to find out if there's a whole, a horizontal asymptote, vertical asymptote, and then our x and y intercepts. So first up, we have a common factor, x minus 2 on the top and bottom. In any time that happens, we initially start off by saying x minus 2 has a common factor. Therefore, at x equals 2, we have what we call a whole. That's going to be a small opening in the graph, allowing us to have a space. From here on out, the only part of this problem we'll evaluate now is the graph of x plus 1. So we no longer have a denominator, and so therefore we have no horizontal asymptote either. The vertical asymptote is now gone because it turned into a whole, so we don't have a vertical asymptote either. Our x-intercept is found by setting the numerator equal to 0, and we get an x-intercept at -1. So we will cross the x-axis at -1, 0. Last, we have a y-intercept by plugging in 0 for all the remaining x's. So 0 plus 1 equals 1. Therefore, we have a y-intercept at 0, 1. Really, we know that this is a linear equation, and we'll want to go back and put an open circle at 2. Let's evaluate the next function that I have here. This time, notice that the denominator is squared. So initially, many of you will go ahead and say there's a whole at x equals 2. But notice that we still have another term in the denominator. Therefore, x minus 2 equals 0. X equals 2 has now turned into a vertical asymptote. Because a vertical asymptote is an infinite discontinuity, we ignore the whole. Even though algebraically it did show up on the graph, it's no longer going to show up as a whole because the vertical asymptote is more powerful. Next, I notice that I have an x term on top and an x term on bottom, and because they are the same, I have a horizontal asymptote at y equals 1. To find my x-intercept, I set the top equal to 0, and again, we get an x-intercept of -1. And to find my y-intercept, I plug in 0 for all the remaining x's. And in this case, I get -1/2. So 0, -1/2 is where we cross on the y-axis. Let's jump to the next slide and just take a look at the graph. So again, notice we ended up in this first problem having this show up as a whole. Now, notice that there is an opening in the graph, and the only part of the graph that we see is really the graph of x plus 1. Crossing at that +1 and on the x-axis at -1. In the second equation, remember we initially thought we had a whole at x equals 2. But because there was an additional factor in the denominator, that turned into a vertical asymptote at x equals 2. We also still had our x-intercept at -1, and we have our y-intercept happening at 0, -1/2. Also, you can see on this graph that we have our horizontal asymptote taking place right here at that value of 1. So just a quick recap. Today we talked about different ways of analyzing rational functions, how to find the x-intercepts, y-intercepts, vertical and horizontal asymptotes, but the big idea was evaluating vertical asymptotes, and the limits around them to get a better idea of what the graph will look like. I hope to see you soon. Bye.